Hi, this is a walkthrough of, let's see, I think we're doing questions 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17, and 18, oh, and 19, okay, of the spring 2019 final from a 265. This is in preparation for exam 2. And in fact, if you've been working on the exam that Dr. Park published, whether or not you're in his section, one, it's a pretty good set of questions to go over, but I'm just now realizing that most of his questions are directly taken from this exam, which makes a lot of sense. It's the most recent final. But I'm pretty much recording a lot of what I did last night, so that's, it could be more interesting. But anyway, question 8, let's get going. Let A be an m by n matrix. Which of the following statements is necessarily true? Whenever you see a bunch of statements about nullity and rank and the column space, the null space, the row space, all of that jazz, one important or obvious answer choice to look for is one of these facts that should be drilled into your brain by now, and that's that the rank of A is the same as the rank of A transpose. And would you look at that? B is there. That is our correct answer. Sometimes it just is that easy, and as long as this fact is ingrained in your skull, some of these questions are much easier as a result. Question 9, which of the following is a basis for the null space of A? Let's just go through this. This is a lot of algebra. 3, 2, 3, 1, 3. I'll line these up a little bit better. 3, 1, 2, 2, 2. Okay, let's subtract 3 row 1s from row 2. 0, -4, -3, -3, that's weird, 3, and -5, and subtract 3 row 1s from row 2. We will get -4, -4, -4, and a -5 here. I'm going to flip the sign of row 3 and row 2, and we're going to subtract row 2 from row 3. That will leave us with 1, 1, -1, 1. Let's subtract 4, no, not yet. Let's subtract 2 row 1s from, 2 row 3s from row 1. That'll give us 0, 0, 4, 0. Let's subtract 4 row 3s from row 2. That will give us 0, -1, 9, -1. And let's see, we're almost done. To get a little bit of a sense of what positions we're missing, I'm going to rearrange things. And okay, that's the last thing we need to do. We're going to flip the signs on row 3 and add it to row 2. That will give us, when I said add, I meant subtract. 0, 8, 0. Okay, and now we're ready to solve. So we see that we can express this in terms of our free variables, where x1 plus 4x4 is equal to 0, x2 plus 8x4 is equal to 0, and x3 minus 9x4 plus x5 is equal to 0. So we can express these in terms of two vectors for x4 and x5. We have an x4 vector, which is composed of, x1 is equal to 4x4, x2 is equal to, we have to move these over to the right-hand side. So x1 is equal to -4x4, x2 is equal to -8x4, x3 is equal to 9x4, x4 is equal to 1 of itself, and 0x5s. And then we also have x5, which is not dependent on x1, 2, or 3. It's equal to -1 x4 and 1 of itself. And sorry, I didn't mean x4, I meant x3. It's in our x3 equation here. x4 is one of our other free variables. So by definition, it's not dependent on anything. Okay, but A. A is our correct answer. If you take these two vectors, we can consider them the basis of the null space there. Okay. Question 10. Suppose a 3 by 3 matrix A composed of all those components has a determinant of 4. What is the determinant of this guy right here? We know some basic rules for this. Whenever we multiply a row or a column by some factor, and I'm not sure why I'm writing this out. I'm not writing the whole sentence. Whenever we multiply a row or a column by a factor, it will multiply the determinant by that factor. Whenever we add a factor of a row or column to another row or column, it will do nothing to the determinant. Whenever we transpose a matrix, it will do nothing to the determinant. And whenever we switch the places of two rows or columns, it will do, well, sorry, I was about to say it'll do nothing, but it will change the sign of the determinant. So let's figure out what they've done here. We see that they've added a row to another row here, and we know that that will have no impact on the determinant whatsoever. So we can actually just get rid of that right off the bat, and the determinant of B will not have changed. We see that they've multiplied a column by 2. So we know that in order to get from A to B, our determinant must have been multiplied by 2. I'm actually going to keep track of it down here. So we started with 4. We have to multiply by 2. And then what else have they done here? Well, A, B, C are in the correct positions, but D, E, and F, and G, H, and I have been flipped. So we need to exchange rows 2 and 3. That will multiply our determinant by -1. And at this point, we are done, because if we flip these rows, and we've already dealt with all the other operations that took place, we have our matrix A. And so if we need to take matrix A, which has determinant 4, these are the steps, or the changes that we made to the determinant to get to the original matrix B. 11, let's compute the value of this determinant right here. So like always, I'm going to write out our nice little plus, minus, plus scheme. I did that same thing last time. Minus, plus, minus, plus, minus, plus, plus, minus, minus, plus, plus, minus. Okay, and that's our guide for how we're going to sign some of these guys. And give me 1 second. I'm going to, too many things near me are giving me notifications. There we go. Okay, so this is going to come in handy in just a sec, because instead of taking this 4x4 determinant using a full cofactor expansion, which would be absolutely terrible, what we can do is multiply 2, because 2 is in a column of all zeros, we can multiply 2 by the submatrix that we get by crossing out the row and column that 2 is in and take the determinant of that instead. So we're left with 2 times the determinant of 0, -5, 0, 3, 0, 5, -4, 3, -7. And already things are much easier. In fact, we can do one further step by taking this -5 that's in a column by itself, taking that guy out, making sure to note to take into account the sign that position will have, and we're left with 2 times -5 times -1, because it has a negative sign at that position, and we are going to be left with the determinant of the matrix formed by crossing out the row and column that 5 was in. We have 3, -4, 5, -7. This determinant will be -21 plus 20, so -1, and we are left with, well, these two -1s will cancel, and we're left with -10, which is our solution. 12, suppose that A is equal to P inverse multiplied by D multiplied by P, where P is a 3x3 invertible matrix and D is given there. Let B be 2i plus 3a plus a squared. Which of the following is true? So we know that since P is an invertible matrix and D is a diagonal matrix, we know for a fact that D here encodes the eigenvalues of A, and that A, because we can find a diagonal matrix P and an invertible matrix, a diagonal matrix D and an invertible matrix P, such that this whole relation is true, A is diagonalizable. We have diagonalized A right here. And essentially what this question is asking you to do is to know or recall a couple facts, which they really didn't teach us as far as I can tell, at least in my lectures, and I had to go find on my own, but that's fine because we know them now. We know that if lambda is an eigenvalue of A, that lambda squared is an eigenvalue of A squared. That's the first hint that's going to help us out a lot here. Also, if lambda is an eigenvalue of A, then C times lambda is an eigenvalue of CA. And then finally, well, actually, sorry, there are two more. Lambda 1 plus lambda 2 is an eigenvalue of A plus B if lambda 1 is one of A's eigenvalues and lambda 2 is one of B's eigenvalues. And then finally, we can use that fact to see that lambda plus C is an eigenvalue of A plus C times the identity matrix. And so we know that if when we find what the matrix B could be, if the matrix B has three distinct eigenvalues, it must have three distinct eigenvectors and therefore be diagonalizable, and that its new eigenvalues will show up on the main diagonal, as in these two examples, of the matrix C, the diagonalized version of B, which will encode those new eigenvalues, like I think I just said 10 seconds ago. So let's figure this out. We know that the eigenvalues of A are 1, 2, and 3. So A has lambdas 1, 2, negative 3. So A squared has lambdas 1, 4, 9. Also 3A has lambdas 3, 6, negative 9, and then we can finally solve for the lambdas of A squared plus 3A plus 2I, and we'll see that will all come out to 6, 6 comma 12 comma 2, because the sum of these two first operations, if we just had a B that was composed of A squared and 3A, our eigenvalues would be 4, 10, and 0, but then we have to factor in the 2I, and we add 2 to all of these eigenvalues. So because B has these three, that's the eraser. Because B has these three distinct eigenvalues, it must be, by definition, diagonalizable. And because it's diagonalizable, when diagonalized, it will have a matrix C that encodes its eigenvalues down the main diagonal. So B is our correct answer. 13. Which of the statements, the following statements are true? 1. If lambda is an eigenvalue for A, then negative lambda is an eigenvalue for negative A. Let's just choose a very simple answer for this one. Not answer, but a very simple explanation. I don't have a rigorous proof for this one. I'm sure you can find one online if you feel that you're lacking. Let's just use the identity matrix here and find its eigenvalues. Its eigenvalues are going to be 1 minus lambda squared is equal to 0, or lambda equals 1 with a multiplicity of 2. But we'll see that if we take the negative identity matrix, remember that won't flip the sign on lambda because we're adding negative lambda I into the A after we've already inverted it. That will give us negative 1 minus lambda quantity squared equals 0, which is solved by lambda equals negative 1. And this is a more general case. Sorry, this is not a more general case, but if you want to try this with any number of potential n by n matrices, you will see that this does in fact hold. So 1 is good. 2, if 0 is an eigenvalue of A, then A is not invertible. You can think about this numerically, but I like to think about it a little bit geometrically. If 0 is an eigenvalue of A, we know that what an eigenvalue means geometrically is the factor by which elements on one of the eigenvalues are scaled when you apply the transformation. So let's graph this out quickly just as a little example. Let's say that we had some matrix with an eigenvector of 1, 1, whose corresponding eigenvalue was 0. What this means is that every single vector along this line, when we apply the transformation, will go from its original position to the origin. And there are multiple ways of continuing this explanation, and I just did a particularly bad one that I cut out. Hopefully you didn't notice that. But what you can take this to mean is that the null space is not going to be zero-dimensional. The null space will have at least one dimension if there is some eigenvector, an eigenvalue who together squish all of their corresponding values onto the 0 vector, because that will mean that there are non-trivial solutions for AX equals 0. And what that means, if we kind of follow the road down a little further, is that there is no way for there to be a pivot in every row and column of our n by n matrix, because if there was, then our matrix would be full rank, and the dimension of the column space would be equal to n, and the dimension of the null space would be 0. And because the dimension of the null space in this case is not 0, it means that one of the elements of the main diagonal of our reduced row echelon form of A is 0, and therefore it is not invertible. So that's a very long-winded explanation for that, but hopefully that gave you a little bit more of an idea of what's going on, at least in my head, maybe not in linear algebra as a whole. Option 3, if an m by n matrix A is diagonalizable, then A has n distinct eigenvalues. So this is incorrect. If A has n distinct eigenvectors, then it is diagonalizable, and you can kind of think of that, store that as a fact in your head by remembering that A is only diagonalizable if its eigenvectors span R to the n, if they span the input and output space of that matrix. And this kind of makes sense because we know that in order for a set to span a certain space, it has to have, or it must have at least as many vectors or elements as the dimension of the space that we're in. And so, yes, we would need n distinct eigenvectors, not n distinct eigenvalues. Because remember, we can have fewer eigenvalues, but as long as each of those eigenvalues, if their corresponding eigenspace, say, has multiple vectors in it to make up for that, we can still be diagonalizable. And by check, I meant X. And finally, 4, let A equal that matrix there. A is both invertible and diagonalizable. Well, it's definitely invertible, as its determinant is 4, but is it diagonalizable? Let's test it out. We're going to solve 2 minus lambda equals 0. We see that lambda equals 2 with a multiplicity of 2, and when we plug in lambda equals 2, we will get the matrix 0, 0, 0, not 0, 0, 0, 0, 0, 0, 0, 1, like so. And right off the bat, we see that this, the eigenvector that we'll slightly rewind. We will only get one eigenvector from this matrix right here. And just like we were saying earlier, if we have only one eigenvalue for, let's say, a two-dimensional matrix like what we're dealing with here, we would need this eigenvector to correspond with two different, this eigenvalue to correspond with two different eigenvectors in order for us to be diagonalizable, because we need our eigenvectors to span all of R2. In this case, they don't, so we're not diagonalizable, and 1 and 2 are correct. 14, define a transformation from R2 to R2 by T of x is equal to AX, where A is given there. Which of the following is a basis B for R2 with the property that the, I said B, I should have said beta, the beta matrix for T is a diagonal matrix. So really what this question is asking you to do in a very roundabout way is to find an eigenbasis. And the eigenbasis is going to be a basis composed of the eigenvalues of the matrix here, which is defining our transformation. And that's important because we know that along an eigenvector, I can never remember whether I said eigenvector or eigenvalue. If I just said eigenvalue back there, I should have said eigenvector, composed of the eigenvectors of this matrix up here. And we know that along eigenvectors, elements only, or vectors only get scaled. They do not get kicked off their own span as a result of the transformation taking place. And that means that the beta matrix for T, which I'm still not too sure what a beta matrix is, but it will be a diagonal matrix. We're doing a very roundabout diagonalization here through a transformation. So we're going to solve 2 minus lambda, 3 minus lambda, negative 1, negative 6, finding the determinant of this, where the determinant is equal to 0. That will be lambda squared minus 5 lambda plus 6 minus 6 is equal to 0. These terms will cancel out, and we can factor lambda minus 5 is equal to 0. So lambda is equal to 0, lambda is equal to 5 there. And so if we plug these two in, we should be able to pretty quickly get our eigenvectors. So if lambda is equal to 0, we have 2, negative 6, negative 1, 3, which we can simplify down to 1, negative 3, 0, 0. And the eigenvector that we will get from this, I'll put it over here actually with our answer choices. The eigenvector that we get from this is going to be 3, 1. Okay, secondly, if we choose lambda equals 5, we will have negative 3, negative 2, negative 1, negative 6, and we can simplify this down to 1, 2, 0, 0, and the eigenvector that we will get from this is negative 2, 1. And so these two together form an eigenbasis for the transformation defined by the matrix A. And so that is our answer choice A. Question 15, let A equal that complex valued or imaginary valued matrix there, where I is the square root of negative 1, and we're trying to find a to the 32nd power. I'm pretty sure you can do some fancy diagonalization stuff to make this much easier, utilizing the fact that a to the k is equal to p inverse d to the k p. And that will get you an answer pretty quickly. But just because I feel like it, we're going to brute force our way through this one and see how it goes. So we know that a to the first power is equal to 0i 0, and if we're looking for a to the second power, we're just going to multiply a by itself, and that will give us negative 1, 0, 0, -1. If we're looking for a cubed, and I'll just write out the other ones, that's a very bad 4. If we're looking for a cubed, we're going to multiply a squared, I need more space, a squared by a. Let's bring that back down here. And when we do this, we're going to get -I, 0, 0, -I. And then finally, because it actually is the last step, we're going to multiply a cubed by a, which will give us 0, 1, 1, 0. And we are actually done. I'll save a little bit of time by letting you know that if we multiplied this a to the 4th by another a, we would end up back at the beginning, or with a matrix that's equivalent to a to the 1st power. So we know that, if we were looking for a to the 7th, that would land us back here at a to the 3rd. And if we were looking for, say, a to the 16th, or how about the 17th, we would end up on matrix 1, because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 lands us back on the first one, if you want to count it out to make sure. But what this means is that a to the 32nd, because 32 is divisible by 4, that will end us up at matrix 4 here, which is, oh, did I mess this up again? Yes, I did. This should be 1, 0, 0, 1. That's a silly mistake right there. Okay, but our answer is C. If you get the diagonalization to work on this one, I'm still not too confident with imaginary eigenvectors. If you get it to work, let me know. Send me a thing, and I'll update this. 16, consider the dynamical system. I still don't like that they use the word dynamical here. It doesn't seem real. X squared, it's been a long day. X prime is equal to AX, where A is given there. What is the origin? So really what we need to do is figure out what signs our eigenvalues are, because if both of our, let's see, if lambda 1 and lambda 2 are greater than 0, we have a repeller. If lambda 1 and lambda 2 are less than 0, we have an attractor. If lambda 1 and lambda 2 are imaginary, purely imaginary, we'll have a spiral point. And if lambda 1 is greater than 0 and lambda 2 is less than 0, we will have a saddle point. And so with all these rules, we can get to solving. We will have 1 minus lambda, and then multiplied by negative lambda, minus 2 is equal to 0. This will give us lambda squared minus lambda minus 2 is equal to 0. And let's see, can we factor this? This will be lambda, not lambda 2, lambda minus 2, lambda plus 1 is equal to 0. I did, yes, okay, that works. And so this means that lambda is equal to 2 and negative 1. And we see that because one of them is positive and one of them is negative, we will have a saddle point. So C is our answer for 15. And by 15, I meant 16, but it was also C for 16. 17, which of the following is the solution to the differential equation given here with an initial condition? And pretty much we are going to start off with the exact same solution process where we are finding our eigenvalues and eigenvectors. And remember, this whole thing can be expressed in the same way that they did up here, which is, a way that I'm a little bit more comfortable with, which is x prime equals some matrix multiplied by x. Okay, so we have 2 minus lambda, 1 minus lambda, minus 6 is equal to 0. This will give us 2 minus 3 lambda plus lambda squared minus 6 is equal to 0. Let's see, I'll do it over here. Lambda squared minus 3 lambda minus 4 is equal to 0. And this is the same thing as lambda minus 4 lambda plus 1 is equal to 0. So lambda is equal to 4 and negative 1. When lambda is equal to 4, our matrix will be negative 2, negative 3, negative 3, not negative 3, positive 3, and 2. This will give us a simplified matrix of 1, negative 1, 0, 0, and therefore an eigenvector of 1, 1. And so I'll just be clear, this corresponds to lambda equals 4. For lambda equals negative 1, we will get 3, 2, 3, 2, which will simplify down to, well, 3, 2, 0, 0, which gives us an eigenvector, of negative 2, 3. Is that correct? Well, this would be negative 2 over 3, 1. So yes, negative 2 and 3. Okay, good. And we are almost ready to solve things. We can set up our solution as x of t is equal to c1 multiplied by the eigenvector corresponding to, let's do lambda equals 4 first, so 1, 1, e to the 4t, where we're using e to the lambda t, putting the eigenvalue in the exponent there, plus c2 times negative 2, 3, e to the negative t. But we have an initial value here, x of t, where they're using x up here, but I'm using x of t to represent x1 and x2. The x of t begins, for x of t is equal to 0, at 5, 0. And because t is equal to 0, that's going to get rid of both of these components, and we'll be able to solve for c1 and c2. We can set this up as a matrix, 1, 1, negative 2, 3, 5, 0. So this matrix here is equivalent to, let's subtract row 1 from row 2. We have 1, negative 2, 5, 0, 5, negative 5. We can simplify this down to 1 and negative 1, and add 2 of it to row 1 to cancel this out. Add 2 of it, that's 3. And those are our solutions. C1, oh, there goes my cover. I did have to do a cut there. C1 is equal to 3, and C2 is equal to negative 1. And so at this point, we should be able to solve or identify which of these answer choices is correct. If we take a look here, if we change this to a plus and then flip the sign of both of these terms in here, we are left with exactly option B. Let's see if that's correct. 17 is B. And this is interesting because this is the first time I've done this problem. You almost never see when I'm recording something. Usually I've done it upwards of 5, 10 times for any given problem. But this one I just saw, and I had done the homework for it earlier today, so I figured I might as well give it a try. Oh no, we have 2 more problems. I thought we were done. I was giving my end of video spiel, but no, we have more. Which of the following subsets of the vector space R3 is a subspace of R3? So in order to be a subspace, we have to be closed under vector addition, scalar multiplication, and we have to contain the 0 vector. So the set of all vectors V such that 2xyz is equal to 0, well, that's just going to be the coordinate planes xyz. So, if we draw out our little first octant graph, that's going to be the set of all vectors in the xy plane, the xz plane, and the YZ plane. And that's no good because if we take a vector in this plane and add it to a vector in that plane, you will get a vector that's kind of coming out of the page up in the first octant itself, not just on one of the coordinate planes. So this first one is not closed under vector addition, so that's no good. What about option 2? The set of all solutions to that equation right there. Well, that's great. We can express that as a span, but also geometrically it's the shape of a span. It's a plane that passes through the origin, and we know it passes through the origin because there's a solution for xyz is equal to 0. Xyz is equal to 0 solves the whole thing, and so in the end, you can go and check if it's closed under vector addition or scalar multiplication, but it will be because it's a plane and it passes through the origin. That's just one of its properties. So that is good. What about 3? Well, we can express this guy as a span too, and also this is just a null space. We can set this up as AX equals 0, where A is this matrix here. X is our set of variables, and our zero vectors right there. And we know that a null space 1 can be expressed as a span, and 2 just is a subspace in itself. It's one of the 4 main subspaces. So that is in fact a subspace. What about 4? The set of all solutions to this plane right here. Well, no, that is no good at all because it does not pass through the origin. If we were to graph this in the first octant extremely sloppily, xyz there, we would see that it crosses the x-axis at x equals 1, the y-axis at y equals 3, oh well, and the z-axis at z equals -2. But either way, you can see the plane spans between these 3 and extends infinitely in all directions. It never touches our origin there. And you can plug in 0, 0, 0 and see that you will get 0 equals 1, which is a contradiction. So this guy is no good. So 2 and 3 are our correct answers. And I'm just going to go check. 18 is A. Yes. Okay, 19. Let's determine a basis for the set spanned by these vectors. So really, we're looking for the basis of the column space of these vectors, which is going to be formed by the vectors which correspond to leading ones in the row echelon form. The row echelon form of the matrix formed by smushing all these guys together. So let's do that. 1, 3, 1, 5, 2, 2, 2, 6, 3, 11, 7, 0, 3, 9, 5, 17, 12, 0. This looks like it's going to be a lot of fun to deal with. I didn't want to make it bigger. Let's duplicate and get to work. Let's subtract 2 row 1s from row 2. 0, 0, 1, 1, 3, -4. And let's subtract 3 row 1s from row 3. 0, 0, 2, 2, -6 is 6, minus 6 again is -6. We can divide all this by 2. I'll always forget if I do that. We'll get 1, 1, 3, and -3. We can subtract row 2 from row 3, and we will get 0, 0, 0, 1. That's convenient. And we see that we have 3 leading terms here, 3 pivot positions, and those correspond to vector 1, vector 3, and vector 6. So 1, 3, and 6, E for 19, is our correct answer. Okay, hopefully you learned something. I actually like my explanations for some of these questions a lot better than the ones that I recorded last night for the exact same question. So just goes to show you this this practice does end up helping in the end. Okay, bye.